What if the entire quest for perfection was flawed from the very start? Today, we're going to dig into two massive ideas, one from the super abstract world of logic, and the other from, well, the rugged, messy shapes of nature. And what they both show us is something pretty profound. Our universe is way more complex and, honestly, more beautifully imperfect than we ever imagined.
All right, so let's start with a puzzle. What in the world could a mathematical proof and a coastline possibly have in common? I know, it sounds kind of random, right? But the answer connects two of the biggest, most mind-bending intellectual revolutions of the 20th century. One happened in the super clean world of pure logic, and the other, well, that one happened in the messiest parts of the real world.
Okay, so to really get why these ideas completely rocked the boat, we need to jump in a time machine and go back to the early 1900s. You got to understand, this was a time of just immense optimism. People really believed that science and logic were on the verge of explaining everything, like everything, perfectly.
And this wasn't a new idea. This dream of a perfect, totally provable system had been around for centuries, literally millennia. I mean, all the way back to the ancient Greeks, the goal was to build all of our knowledge on this one solid, flawless foundation. And that whole quest kind of reached its peak with this enormous work called Principia Mathematica. This thing was a massive effort to build all, and I mean all, of mathematics from just a few simple starting points, a few axioms, with absolutely zero room for doubt.
Just stop and think about that for a second. What that really means. If you could prove every single true statement, you could basically solve the universe, like a giant cosmic crossword puzzle. Imagine a world with no weird paradoxes, no gaps in what we know, no questions that are truly, fundamentally unanswerable. That was the dream. That was the ultimate prize.
But then, well, that incredible ambition hit a brick wall, a huge one. In 1931, this quiet 25-year-old academic in Vienna, a guy named Kurt Gödel, he publishes a paper. And this paper just sent shockwaves through, well, everywhere. Math, philosophy, you name it. In an instant, the dream of perfect, absolute certainty was over. Just like that.
And for a lot of people, finding out about Gödel's work was just one of those, life-changing moments. The author, Douglas Hofstadter, he talks about this perfectly. He says he just stumbled on Gödel's proof as a teenager, and it just completely blew his mind. He realized that the world of logic, this perfectly ordered place he imagined, was not at all what he thought it was.
So how did he pull this off? Well, to get the gist of it, let's look at a really old puzzle, the liar's paradox. It's the sentence, "This statement is false." Think about that. If it's true, then it has to be false. But, okay, if it's false, then that makes it true. You see, it's this perfect, unbreakable little loop that just ties your brain in an...
Okay, now here's where the real genius kicks in. Gödel created a mathematical statement that was a clever version of that same paradox. But instead of saying, "I am false," his statement basically said, "This statement is unprovable." Unprovable, that is, using the rules of the system it's in. So, what happens when you try to prove it? What do you think?
Let's walk through this. If you could somehow prove the statement is true, well, then you'd be contradicting what it says, right? It says it's unprovable. So for the whole system of math to stay consistent, the statement has to be unprovable. But wait a minute. If it's unprovable, then the statement, "This statement is unprovable," is actually true. And boom, Gödel found a statement that was true, but could never, ever be proven by the system. It's like he proved that logic itself has a permanent blind spot.
So, okay, logic has limits. It's not perfect. But what's really wild is that a totally similar breakdown of this perfection idea was happening at the same time, but in our understanding of the physical world. And the problem here wasn't with some abstract proof. It was with something as simple as a ruler. How long is a coastline? I mean, sounds like a straightforward question, doesn't it? But a mathematician named Benoit Mandelbrot used this exact question to show us how incredibly wrong our simple assumptions about the world can be. Because the answer, it turns out, totally depends on how you measure it.
Okay, picture this. You're trying to measure the coast of Britain. You start with a giant 100-kilometer-long ruler. You lay it out and you get a number. Fine. But you've missed all the little bays and curves, right? So now you switch to a 10-kilometer ruler. You can now get into those curves a bit more, and suddenly the total length is longer. Then you use a 1-meter ruler. Now you're measuring around individual rocks, and the length gets even longer. The smaller your ruler gets, the more wiggles and zigzags you find, and the length just keeps growing and growing all the way towards infinity. It's nuts.
What Mandelbrot showed everyone was this fundamental mismatch. You know the perfect shapes we all learned about in geometry class? Circles, squares, straight lines, they're all nice and clean and simple. But nature? Nature's not like that. A coastline isn't some smooth, elegant curve. No way! It's messy, it's rough, it's jagged, and it's infinitely complex.
So if our old geometry totally fails at describing the real world, what do? Well, Mandelbrot's answer was brilliant. He said, let's stop trying to fight the roughness. Let's stop trying to smooth it out. Instead, let's invent a whole new kind of math that's designed to embrace it. And he called these new shapes fractals. And the key idea, the real magic behind them, is something called self-similarity. All that means is that if you take a fractal shape and you zoom in on any little piece of it, you'll see the same basic pattern, just repeating itself over and over and over again at smaller and smaller scale.
And here's the cool part. Once you know what you're looking for, you start seeing fractals everywhere. Seriously, the way a big tree branch splits off looks just like the way a tiny twig splits off. The jagged silhouette of a mountain range looks like the jagged edge of a single rock. This wasn't just some abstract math game. This was the hidden blueprint, the geometry of the natural world itself.
So this was a massive shift in how we see things. We went from looking at the world through the lens of these simple, perfect, idealized shapes to finally having the tools to appreciate the intricate, repeating, infinitely deep complexity that actually defines the world we live in.
Which brings us all the way back to that first question we asked. What do a mathematical proof and a coastline really have in common?
The answer? They both show us the limits of perfection. See, just like Gödel discovered these truths that were real but forever unprovable, hiding deep inside of logic, Mandelbrot discovered this infinite complexity hiding in the simple shape of a coastline. Both of them, in their own way, completely shattered that old dream of a simple, clean, totally knowable world. And what they gave us instead was something, well, something way more interesting.
And I think that's the real big idea here. That flaw in perfection, it wasn't a flaw at all. The incompleteness of logic, the infinite roughness of nature, those aren't bugs, they're features. They're fundamental parts of how reality works. The universe isn't some simple puzzle waiting for us to find the last piece and solve it. No, it's a place of endless, mind-boggling depth and detail.
So where does that leave us? Well, with this fascinating idea. In the world of pure logic, and in the messy, real world of nature, it seems the closer we look, the more complexity we find. And it really makes you wonder, was the goal ever to find some final answer? Or maybe, just maybe, it's always been about the journey, about appreciating the incredible, infinite process of discovery itself.